Hello everyone, welcome back. Today we are going to discuss another room on TryHackMe and its AI models and data. We are going to learn how the data is fundamental to the AI security and how the models power it. And it's a room on the AI security pathway. It's just recently released by the TryHackMe and I'm going to try to cover all this. But for now, let's start with this room, AI models and data, and let's start with the task number one. Uh, every AI model is at its core a product of its training data. Before a single prediction is made or a single prompt is generally answered, decisions about what data to collect and where to collect the data from and how it processes have already shaped everything about what the LLM model will ever do. And those decisions generally carry security implications that most organizations deploy AI today, and they have never been examined. So there is a security element as well when we are training the data. A lot of we aren't cautious about what the data is, what on what data the model is trained. So there is an element of security we will discuss as well from PII, which is personal identifiable information. Sorry if I pronounce it not. Personally identifiable information is any representation of data that can be used to identify an individual directly. Anything that could be recognized for any personality is personally identifiable information, and it's scrapped from the open source, open web, and it could contain any data that is available on the internet, and it could be containing credentials that is generally given to the LLM during its training, because the LLM is trained on a large amount of data, and it could be containing anything related to the personality, so which could be any PII, which is personally identifiable information. So there is generally are a lot when a model is being deployed. It could be containing sensitive information, could be containing anything that it is not bound to show. So we generally use fine tuning to overcome this, and we are going to discuss that as well. So it's introduction. They begin long before in a data supply chain that is often invisible, poorly documented, and almost entirely unaudited. What this means is generally we aren't given any such importance to the data being fed to the LLM. It needs to be filtered, it needs to be evacuated, and yeah. So we have the following learning objectives. We are going to understand where the AI training data generally comes from and the security risks that are introduced by the poor data provenance and provenance. Sorry if I pronounced it wrong. And we are going to recognize how the PII and the sensitive credentials can become permanently embedded in the model weights through the large scale web scraping. And we are going to understand how key model building decisions, overfitting, quantization, and federal learning each introduce distinct security risk, and we are gonna cover it anyways. Don't be fed up if this isn't familiar to it. We are gonna cover it. So we are gonna understand the inheritance problem and what organizations unknowingly take on when fine-tuning pre-trained models are done, and we are going to recognize why trained models are big black bones and what model parts do and what they fail to do, and we are going to address this. And there is a general recommendation from TryHackMe to cover up the AI and machine learning security threats room before jumping into this room. Anyways, we are going to check up these box and jump onto the task number two. So and the training data in the AI and machine learning security threats. Now we walked through the machine learning lifecycle and established that before a model can be trained, data must be collected and cleaned. The important term over here is the clean, because there is a lot of data which the model is trained, and if we are training an LLM for any particular purpose, then we need to clean the data, and for any legal restrictions, for any nothing that is illegal, for any PII, for any personally identifiable information, for any API keys, we need to clean this up. And that sounds really orderly, so enough. It's done in an order. What this means, its lines, and but let's slow down and ask the questions that the life cycle diagram doesn't answer. So what does the data, from where the data is collected, and who clean this data for the purpose? And you will see the answer generally carry the significant security implication, since we don't know that that's a really sensitive data anyways. If um, I mean, what I mean to say is that sensitive data, if fed into the LLM, would be given to the user using that LLM, and which could be personal harm for that personality if it was PII that was revealed by the LLM, or it could be an API key or anything that is illegal. So the who clean that data is an important step. So it should be having some security implications that sensitive information shouldn't be given, and the most of the organization generally using AI today have no idea what they are, and what who cleaned this data, what the data is, what the data was even on which the LLM is trained. So there is a question that where does the data actually come from, and training a large language model requires a really huge amount of text, and there's a nice example given by the TryHackMe that GPT-3 model was trained roughly on 570 gigabytes of filtered text. What they consider to be modern standards, and the modern standards mean that filtering up anyways on the huge chunk of data, huge amount of data. So yeah, the huge amount of data, where does this come from? We are going to discuss it here. The sources of these huge amount of data, and the huge amount of data which was ultimately filtered to 570 gigabytes by the modern standards filtering. So there is one source which is web scraping, and what it is the automated crawls of public internet content. What this means, it either we use an automation means that it's either a program that's doing the things on its own for the particular purpose, and for the web scraping it means that it's an automated approach that most of the computers are written. We write a program and that scraps all the internet informations, and for the particular purpose, it could be news, forums, blogs, social media, and anything, and it's automated. Meaning, we write a program and the computer, we tell what to do, and the computer does that on its own. And the trust profile over here is low, since there is no version control, and anything could be fed up directly, and we don't have much control over the data. And the trust profile is low, anything sensitive could be fed as well. Since we are using an automated approach, we could filter, but anyways there are general limitations what eventually could be better than human filtering out. And yeah, so we can't do it that filtering as a human on its own, since it's a really huge amount of data. You can consider by the fact that GPT was trained on much more than 570 gigabytes of data. So 570 gigabytes of data is a filter test. It would be 2x more, you can say 2x more times of data, and so you can't just do it on the human approach. And we need automation, but what could we filter? Even we there are certain limitations. We could say that either filter out the user informations and the passwords, the emails, the credentials, but there remains anything anyways. Then the data could be coming from the licensed data sets, and the licensed data sets are data purchased or agreed with the platforms. These platforms, which include the platforms having huge amount of data, OpenAI, which contains huge amount of data, the Meta on a social post contains huge amount of data, Reddit is a great community having a huge amount of subreddits. So, and the trust profile over here on the licensed data sets, it's medium, often unclear, since the users generally rarely give the consent for the AI training, but anyways it's done so without knowing of the user. Then we have the synthetic data, which is what it is. It is AI generated content and used to train for the AI system. For example, let's say that GPT-3 was trained on that 570 gigabytes of data, and another model uses that GPT-3 for getting an output, and that output is used for training that second LLM. And the trust profile is variable. It all depends on the previous LLM that it was trained, either it was filtered or not. So a medium layer of, and AI generated content is generally not valuable for the LLM to feed on its own, since it's an LLM as well. So it could be making up the mistakes, and if it makes further more chances of mistakes. Anyway, so internal corpus and other data source, which includes the company's knowledge bases and support transcripts, anything on the company's infrastructure that can be fed into the LLM for fulfilling its particular purpose. And the trust profile over here is higher, since we are feeding what the company wants to do with the LLM, and it generally don't contains some sensitive information. Like, why would the company feed such a data into the LLM, which is sensitive, and the sensitive credentials aren't here on the in a plain text that could be fed. So yeah, the most widely used training dataset is common crawl, and if I could just show you the common crawl over here we have huge amounts of data which are used for training of these LLMs we are seeing these days. And it's a publicly achievable archive of the web crawl data that has been underpinned essentially every major model family, you name it, and it would be trained on it. You can say you name DeepSeek V2 and it was pre-trained on it. DeepSeek V3 trained on 14.8 million trillion tokens. And if I show you over here, I just you can see that the size, you can by the size of this, these are huge files, and these contains huge amounts of web scraping data. So yeah, we need to filter it up, but yeah, in these are the major sources for training of these huge model families anyways. And GPT-3 is one of the very few models whose breakdown is publicly documented, and 60% of its token came from the filter version of the common crawl, and more recent models lean even more heavily on it, and the keyword is filtered. The important thing I previously discussed as well, the key thing over here is the filter word. How we are filtering these huge amounts of data is another essential role. We shouldn't be giving some plain text credentials, some sensitive information, anything that the model doesn't want the users to give. We need to filter it up, and we need to filter for the purpose the LLM wants to, the LLM is designed. Yeah. And there's a problem of provenance. Sorry if I pronounce it wrong again. And the data provenance is the ability to answer free questions about any piece of training data. The three major questions are: where did data come from, where was it collected, and has it been modified since. So in most of the AI supply chains today, the honest answer to all three is we don't fully know. Most of the major models are essentially trained on the datasets, or the datasets are pre-configured, a pre-trained dataset, again trained on another LLM, and huge composites assembled from hundreds of upstream sources, and where the original attribution has been lost and simplified or never recorded in the first place. Who cares? We just want to fulfill the need of that particular LLM, and we need to train it anyways. So the Data Provenance Initiative audited over 1800 datasets and found that 70% of the licenses on popular hosting platforms were listed as unspecified, and those that were labeled 66% were miscategorized and usually listed as many permissive than they actually were. So yeah, organizations fine-tuning on these datasets often don't know and what they legally have, let alone what actually inside it. So the software security world has been here before. The security, from the security point of view, the SolarWind was an attack that taught the industry that you can't just trust a compiled binary if you don't know what went into it, what the binary is doing anyways. So it could be which is exactly why software bills of materials, which is SPOMs, became a standard practice today, and the AI equivalent to this is machine learning BOM. A documented inventory of data sources, licenses, and personally identifiable information categories. Personally identifiable information, yeah. And filtering decisions adoption is still early, and most organizations deploying third-party models today have And nothing close to this. So we have another over here, which is the personally identifiable information in the pipeline. Sorry. So one of the most direct consequences of the undocumented and large-scale web scraping is that personally identifiable information ends up baked into the models. I previously discussed this problem as well. We need to filter that data. If that data is publicly available, it might be containing any sensitive information too, because ultimately they are users who feed their passwords into some I don't know, some blog post, and it they just give out in the plain text. So it could be possible, or if it involves any code, then it could be possible that for any authentication mechanisms they leave out the username credentials or anything, or the most common practice is the API keys. We Most of the users just leave the API keys in the source code, and model trains on it, and that API is generally given if it's not filtered. So once it's there, it's a very difficult process to remove. Some medical records, personal email threads, forms, posts about the health conditions or the political views, all of it gets swept up if it was publicly accessible at the call time. And the EU and GDPR explicitly requires data minimization, collect only what's necessary, and this sits in a direct tension with the more data is always better logic driving behind the pre-training. What it means that generally feed more data into the LLM, and the LLM is gonna be the really finest model in the sensory that, and this is the theory behind more data is always better theory. Anyways, so the security implication is measurable and concrete, and the Truffle Security Scandal December 2024 Common Pro, which contains 400 terabytes of data. You can see that 400 terabytes of data, what it could be and how huge it is, and what it would be to filter this data. It contained about 2.67 billion web pages and founded nearly 12,000 live, and the verified API keys and passwords were all there. And with the right prompt, a model trained on that data can sometimes be uh, given that sensitive information, and ultimately compromising the user. So this isn't a bug introduced by an attacker, it's a consequence of what went into during the training. So we as an attackers should know what the model is trained on, and it shouldn't be having some sensitive information. It could be expelled out by a right prompt. And a model's behavior is who's a model engineer. A model's behavior is a direct product of what it was trained on. If that data was wrapped without audit, contained with personally identifiable information, or manipulated upstreams, these characteristics become the part of the model, and there's no reliable way the organization deploying it to know. And the data supply chain is real and as exploitable as a software supply chain for organizations right now. It's almost entirely invisible. Anyways, so let's jump onto the question: which term describes the ability to answer where the data comes from, where it was collected, and whether it has been modified. That will be data provenance, if I have the spelling right. And as always, I am really bad in making up the spellings. And data pro yes, I hope, yeah. So what is the name of the most widely used publicly? Oh yeah, that every model family is trained on, that was common crawl. Luckily I know it, I don't know how. So common crawl. What is the AI equivalent of a software bill of so that was AI bomb, yeah. AI ML bomb. Do I need to put the Python ML bomb? Yeah, likely. I don't know. Honestly, I'm doing this room on the first try, since the AI security learning path just launched yesterday. So I haven't done this room previously. I'm going through it. I'm going through it alongside with you. Anyways, let's jump into the task number 3, building the model. The key concepts when we covered the machine learning lifecycle in the AI machine learning security threads, we did it at a high level: data in, model out, Their task zooms into some of the decisions made along the way that have yet to be covered. Each concept generally establishes a foundation for the future security topics. So the goal here is not just to define them, but to understand why they matter from a security perspective. Anyways, there's EPOCHS, EPOCHS. Yeah, you can just pronounce it on your own. Anyways, so it is one complete pass of the training algorithm that through the training algorithm through the entire data set. In practice, models are trained over many epochs. Anyways, the algorithm repeatedly sees the same data, adjusting the parameters each time until it converges on the accurate prediction. Converges. Yeah, sorry if I pronounce it wrong. Anyways, so the catch is that more a pass doesn't always mean a better model. Train for too long and the model stops learning general pattern and starts memorizing the training data specifically. What it means that the model keeps getting to know about the same thing and it just stops learning anyways. And this problem is named as overfitting. An overfit model performs well on its training data but poorly on the other data. For this purpose, these are generally well-defined models, meaning they are designed for their particular purpose. For example, if I had to give you a quick example, this echo is generally a more defined or well-scoped model of the TryHackMe, which is to give the information about hacking, not everything. So yeah, an overfit model performs well on its training data, but so it's quite possible that the echo would be performing well on its training data and it's going to perform poorly on the other data anyways. So this matters for the security because overfitting is one mechanism by which a model can memorize specific details from its training data, and this could be include being sensitive ones and making it more likely to reproduce them when prompted. And overfitting, you feed it again and again, so it's gonna anyways become active out of it, and it's already being designed for a particular purpose, and you are just making it more narrow for the right prompt to give this out anyways. And we have model validation. What this means is to catch overfitting early. A portion of the training data is held back and never used for the training. This is the validation set. At regular intervals during the training, the model is tested on unseen data to check whether its performance is actually generalizing or just improving on the trained example. Validation set means that the training data you just keep a huge, you fill the bucket with most of the data and you just keep some data in your hand and you ask the LLM if he could predict this data, and if he couldn't, then we could just feed that again. So model validation is also another important, and from a security perspective, validation is the quality gate in the machine learning lifecycle. A model that skips through validation is one whose real world behavior is unknown, and such unknown behavior is generally a security risk. Anyways, it also means any biases or anomalies introduced through the compromised training data may go undetected until the model is already deployed. Then we have post-training optimization, which is pruning and quantization. Once a model is trained, it often goes through compression stages before a deployment, so you need to filter out what you want and what you don't want. Pruning is to remove the parameters that contribute little to the prediction, shrinking the model size, and the security consideration is that changes model behavior post-training and is rarely documented in detail. Anyways, one is quantization, which reduces numerical precision of weights, which means that example 8 bits to uh, 32 bits to 8-bit float bits to cut the memory and compare requirements. And the security consideration is can degrade safety aligned behavior. Backdoor defenses tested on a full precision models may fail to detect threats in a quantized versions. So both steps are applied before the after the training is complete, often by a different third party. A team packaging the model for distribution. Research has shown that quantization can silently degrade the safety mechanisms built into the model defenses that were, and the full precision may fail to detect backdoors once the model is compressed. When an organization downgrades a quantized model without documentation of what changed during compression, they are inheriting unknown behavior modifications alongside efficiency gains. So yeah. Then we have federated learning. All the training approaches are covered so far assume that data flows into a single central location for the model training, which is federated learning flips this, and the model is trained across many decentralized devices or organizations. So all the training approaches we have discussed so far assumes the data come from a single central location. It could be that common prod which was the source for the GPT and the other major models. The federated learning is kind of more a different approach, and we use several decentralized devices or organizations with each participant training locally on their own data and only sending weight updates back to the central server for aggregation. And this was designed with privacy in the mind, and hospital sharing patient records to train is a data protection problem, and a hospital contributing model updates without ever sending the records is a much easier conversation. And in that sense, federal learning generally does reduce privacy risk at the at data level. What it does means that, for example, the hospital sharing a patient records to train a model is a data protection problem. For example, this is the data for the patients. You wouldn't be feeding this into the model, but if it's any medical reports or anything, that should be the model trained. And if the model is for the hospital itself for the well-being of the patient, then these are all the medical reports, all the samples, all the medicines that they should be fed. And this is what we call federated learning, which is decentralized across many devices. So the security trades off, however, is that the integrity of the training data process becomes much more harder to verify in a centralized setup. The organization that trains the model controls the data. In a federated setup, participants can submit poisoned local updates, and these can be very difficult to detect at the aggregation stage. So a couple of boring stuff, nothing more important. Here, the last time federated learning is therefore an interesting case study in security trade-off. It solves one problem by distributing control, but in doing so, it creates a different problem. From who controls the data to who controls the aggregation, and can any participant corrupt it anyways? What this means that we were saying that who controls the data, but who controls the saturation, who controls the segregation, who controls this breakdown. So yeah, this is also another security point of view question. So now jumping on to the answers of this task number questions of the task number 4. So which term describes one complete pass of the training algorithm through the entire data set? And that was, if I and yeah, I hate this word anyways. You can pronounce this on your own. I'm just gonna submit this as the answer. And what problem occurs when a model memorizes training data rather than learning general patterns? That was overfitting. Yeah, it just goes through. It performs well through the purpose over. Yeah. Post-training optimization technique reduces the numerical precision of model weights. I guess that was quantization. We reduce the precision of the weights. Yeah. Uh, and the last question: what training approach trains a model across decentralized devices, sending only weight updates rather than the raw data to the central server? That was federated learning. We split up the entire data into what we call aggregation, whatever it is. Sorry guys, my pronunciation is very bad anyways. So jumping onto the task number 4, we have this. Oh, this has a nice diagrams anyways. This brain along with this telescope and this shield and this lock behind it. Yeah, TryHackMe has done an impressive job on this training. Yeah. So the inheritance problem, training an LLM from scratch means assembling trillions of tokens of data, and trillions are a huge number. Acquiring the compute infrastructure to process it and running a training job that can cost tens of millions of dollars for most organizations. That's not a realistic option, and instead, the dominant model for AI development today is to start with someone else. Yeah, just just take the data, or just take the other's hard work. Just enjoy the labor of the other person. That means to use pre-trained model. A pre-trained model is the one that has already been trained on a large general purpose dataset. Yeah, I discussed it. Just use the other models for your own model. Just enjoy the labor of the other model, or yeah, just reduce the cost. So these are the base models: broad language, understanding grammar, facts, reasoning, questions, and word knowledge. They are produced by small number of well-resourced organizations and then made available for others to build, either through open weights, which are Meta Llama family, or through API access, OpenAI and GPT. So then we have fine tuning is the process of fine tuning to train one of these pre-trained model on a smaller task specific data set. And for example, if we take this for 400 trillion animals who are really number, just take the number, and we are a healthcare company, so we would just be narrowing for the clinical documentation, for the medical research, for any medical sample, for any doctor's prescription, for any doctor's advice, for any doctor's diseases, and diagnose for the patient's results, for the patient's well-being, yeah, anything. And that's for fine tuning. What fine-tuning changes? It changes the model's task specific behavior, tone, and domain knowledge. And what fine-tuning does not change? It does not change the base model weights, the billions of parameters shaped by the pre-trained data, and the fine-tuning organization never saw and almost certainly never audited. So yeah. And the inheritance problem, this is where the security concern sits. So when you fine tune or a pre-trained model, you inherit everything that model already contains. So it's quite possible that the other person's hardware wasn't that hard, and he either ways didn't filter the output, and it contained any sensitive information, or it is not legally bound to overcome any ethical laws. So this arises of the problem, and this could include things you cannot see and did not choose. Biases baked in is something that the particular training organization or the entity wants the LLM, but you shouldn't want. For example, the biasness of the reviews, the biasness of the information, and during the pre-trained dataset. So there could be unexpected behaviors by the base model's training carried through. Any safety elements built into the base model is not as a durable factor. So this shows up in three concrete ways: safety alignment erodes, not breaks. The Stanford and Princeton found it that the defense mechanisms of the aligned LLMs can be compromised by the fine-tuning as few as 10 adversely crafted examples as cost of under $0.20. Even benching fine-tuning on legitimate data degraded safety as a side effect. Bennigan. But this Bennigan, I don't know, sorry. So think of safety alignment like a well-worn path through a forest. The model has been trained to follow this safe path when generating responses. Fine-tuning is like adding new paths through the same forest, and even if those new paths are generally legitimate, like teaching a medical terminology, they can gradually substitute the original safe path, and the model hasn't forgotten how to be unsafe. So I previously mentioned the ethical factor, and like if the other person didn't do the hard work, he just wanted to fulfill his duty or his task, so he didn't filter out the ethical jobs, or he just gave out some loopholes on the model status. So you could be just destroying a parallel, and this is the safety alignment. The probability weights have just shifted, making unsafe responses more likely again. The defense mechanisms don't snap, they wear down, and the specialization increases attack surface. The Cisco found that the fine-tuned models are measurably more susceptible to prompt injection than the base models they were fine-tuned on. So I'm going to explain this why it is. So first of all, the prompt injection is making an LLM, a language learning model, which one we are discussing. So prompt injection means to make LLM do unintended and things like giving us the information about unintended things. For example, if it was trained on things something like sensitive passwords or API keys, then it would split out if we it would spill it out if we just ask him what is the user's password, what is this user's password. And the prompt injection is basically that you make that LLM to your purpose and forget him what he was designed on. So the model hasn't forgotten. Sorry, we were on. The reason is structural fine tuning narrows the focus and further narrow of the model for the purpose makes it easier uh, for the attackers for the prompt injection. So think of it this like a fine tuned on the financial reports, get better at financial reasoning, but also becomes more responsive to an attacker who frames their prompt in financial terms. For example, like he could be asking is the uh, what is the bank's financial revenue or anything. What how much money does the bank have? Like, let's consider this basic question: how much money would bank having? So if the LLM was designed on the financial and a huge financial data further narrowed down, so if the user asks it and it's an intended, although we give the prompt injection and the LLM spit it out, so it's a really serious security concern. And the version matters, and it's really tracked. Fine-tuning always targets a specific checkpoint of a base model. If that's a checkpoint later turned out to contain a backdoor or problematic training data, every derivative inherits it, and the version it generally replicates from one to generation to another. As we say that one spoiled child further makes his generation more spoiled. Yeah, it's you can say it anyway. Yeah. So once we train the data on poor set, and the also inherits it. For example, if it's trained on some wrong data, and the other also inherits that wrong data, so it's going to continue on the keys or chains. And the inheritance tag. So when your organization deploys a fine-tuned model, you are not deploying the fine-tuning work your team did. You are deploying the entire pre-trained base beneath it. The base was short, but by a training process you didn't control on the data you didn't audit by an organization whose supply chains you almost certainly haven't reviewed. Fine-tuning is powerful, but it's a huge risk anyways. The questions are what is the process of taking a pre-trained model and constituting to train it on a smaller task specified data. That was inheritance or fine-tuning. It was fine-tuning. Yeah, fine-tuning, and along with that, yeah, which so we have this second question: what term describes a model that has already been trained on a large data set? That would be pre-trained model. And with that, we completed our task number 4 as well. Let's jump on to the task number 5. So models are black box. Black box means that you don't know what is behind it, and white box means that you know what is behind it. So what here it means that when a security teams want to audit a piece of software, they have options. Either the source code is readable, and even compiled binaries can be assembled, stepped through, and reasoned about. Trained model weights are neither, and are billions of floating point numbers, and they carry no human readable record of how they were shaped, what data influenced them, and what behaviors in code. You cannot open a model and find the decision that it makes in a certain way. This is a black box, a complete black box. This means that trusting model is fundamentally trusting the process that produced it. You can test its behavior, you can run inputs, you can give it prompts, you can benchmark it against known tasks and prove it with adversarial prompts. Adversarial, sorry guys again. Adversarial prompts through red teaming, all of these are valuable, that they are sampling, not auditing. They can tell you how the model behaved on the inputs you tried. They cannot tell you what it will do on the inputs you haven't thought of yet. So maybe it might give an unexpected response. Model cards and the documentation artifact are designed to address this. Is a model card, a structured document that accompanies the model and describes what it is and how it was built and wait for it. The concept was introduced by Google researchers in 2019 and has become the closest thing the industry has to a standard transparency format. A well-known and well-formed model card should give you the answers to the questions you can't get by inspecting the weights themselves. So the training data, what sources were used, how they were filtered, the intended use, what the model was designed for, the valuation results, the performance metrics across different conditions and demographics, and the known limitations, the conditions under which the model is known to underperform. The bias assessment where training data evaluation may have been introduced, and the license, what you are legally permitted to do with the model is also a great question. Think of it like a numerational label or for an AI model. You can't see inside the product, but the label is supposed to tell you what went into it and what went to out for it. The gaps, have you ever checked out a food label and it all sounds genuinely good? Do you find your chicken slices are only they are only 49% chicken? Well, in practice, model cards can also be frequently incomplete, vague, or generally, in some cases, absent entirely. Unlike food labels, there's no regulatory requirement to produce one. As of now, it remains voluntary for most use cases. The incentive to be thorough is weak, when disclosing limitations might reduce adoption. The data provenance initiative audit of over 1,800 datasets found documented gaps throughout the AI supply chain, and model guards sit at the end of the same undocumented pipeline. So from a security standpoint, sparse or a missing model isn't an inconvenience, it's a warning sign. It means the organization distributing the model either didn't evaluate it thoroughly enough to document the findings or choose not to share what they found. Either way, the downstream is using the fly behind. In short, the model card is your audit trail. In the absence of one, there is no audit trail, just a black box, and the hope that whoever built it was through the security was through a well documented and was having a general good needs and did all the hard work. Is insecurity is generally hope and you don't control it anyway. See, what documentation artifact accompanies the model to describe what it is, how it was built, and where it falls short? There was this document. I haven't gone through it, so I'm gonna model guard. Yeah, model guard. It should be model guard. I am not wrong. Model guard, and there are billions of floating point that are this weights or parameters. I don't know. Yeah, that make up a training model. So now we are gonna go through the task number 6, which is the practical of this room, and here we are presented with a scenario where we are a security analyst and our team has been asked to evaluate whether this lab is safe to integrate into the internal tooling, and we have to complete a security review of the model card and flag any concerns before we sign off. So our task is to read through the model card files and the sidebar details carefully, and to hover over any suspicious text to reveal hotspots and click them to flag the findings and rate their severity. So I would recommend you to pause down the video here and do this on your own. I am just gonna go through the here real quick. A text classification model designed for the enterprise document routing and categorization, fine-tuned for Enterprise Base 1.1. This model classifies incoming documents into organizational categories such as support tickets, uh, procurement requests, sorry if I pronounced it wrong, compliance queries, and internal communications built for integration into automated document processing pipelines. How to use this code and training data model trained on data curated from publicly accessible web sources including forums, QA sites, and public documentation. The training corpus was assembled to cover a broad range of enterprise communication styles and domain-specific terminology, approximately 1.2 million text. And there is this our first finding, and it would be a medium because of the no mention of PII, and uh, yeah, it would be a medium severity. Now we move further, approximately 445 megabyte, and then document severity. It was using standard entropy loss training. The model. Okay, so this is another. It should be high. Yeah, it's a score of 0.91. And there's this license, which would be low. License listed as custom with no link, no terms, and no contact detail beyond with the organization. Then an organization name. And then we had I've submitted like 3, okay. So we have more, and it would be here. If I try to hover down, I would get into some. Okay, so publicly accessible is also another one, and we are just gonna give it the high rating. UN site engines another high, and the files here we would be having okay, so this size one, it would be having a medium risk, I guess. I'm gonna add to the audit. Let's submit it, and okay, so 4 out of 6 are correct. I need 5 out of 6. Which one is wrong? This second one, acceptable but not and the license is not the okay. So I'm gonna go through it again. I'm really sorry, guys. So this one, so this one and this one are not correct. Okay, I'm gonna go through it again anyways. Can I edit my response anyways? Yeah, so we are just gonna give it medium severity now. Let's just submit, and this one a severity of medium as well. Let's submit, and boom, we got our flag. I'm gonna submit down the flag. And the conclusion, okay, so it's a long paragraph anyways, we completed on the room. So I hope you learned something from it, and uh, make sure to subscribe if this audio helped. Do give a like, and if anything isn't clear, any topic isn't clear, do leave a comment. I will make sure to respond to every single comment on my video. Thanks for watching.